Next, we want to introduce 2.5 Euler's method for systems. So we have done Euler's method for differential equations before. Now we just want to extend the idea, and you will see the idea is basically the same, and the method is pretty easy. Okay, so just quick review what we had before for Euler's method. We had this, and then what we do is we start from 0, we draw the line, or we draw the vector field. Let's see. The first thing is we cut everything from 0 to capital T, the interval, into multiple small intervals. And then we start from 0 and follow the vector field and go to here and recalculate the vector field here. Through this problem, we go step by step towards the final solution we want. Of course, from here you can see we're basically just doing a local linearization. We locally think the differential equation basically gives you a line, and then you follow all the lines. So of course it's not accurate. The real curve is actually a curve. But then if you let the grid to be super dense, you will be able to get this, okay, to be more and more accurate. Then secondly, we find that, okay, the same idea can be summarized as we replace this y prime to be yk plus 1 minus yk divided by h. With that in mind, then what we have here is nothing but an approximation of the derivative. Okay, and of course it has an arrow, because technically they're the same when h goes to 0, but we are taking a finite h. We're taking some h which is more than a certain size. But then we basically set up this scheme. We have the iterations, which is this one is the previous one plus h times f tk yk. And then we can actually get y1 from y0 and y2 from y1 and keep going until we have yn, which is up to the time t we want. So that's what we had for Euler's method for ODE. Now instead what we have here is we are going to have a system. And y prime equals g t x y. From here, you can see it's very easy to do because we have two different variables. So we can define number 1, t0 all the way to tk, as usual. Okay. Number 2, we will have x0, which is the initial value. Okay, and keep going until you have xn, and finally you have y0, which is the initial value, which you go to yn. Then all we need to do is just produce xk plus 1 and yk plus 1 from xk, yk. Then if you know x0, y0, you can find x1, y1, and because you know x1, y1, you can find x2, y2, and just keep going. And the idea is similar. You replace x prime to be xk plus 1 minus xk divided by h, and you replace your y prime to be yk plus 1 minus yk. And then what you can do is you can have the same thing if you just simplify everything. And then you can have something very similar to the one-dimensional Euler's method. Okay, 1 for xk and 1 for yk. Almost the same format. Okay, except you take different functions for f and g, of course, and also your function now actually involves xk and yk, two of them. Okay, if it's completely decoupled, then xk plus 1 and yk plus 1 can be solved separately, because x only depends on x, but now xk and plus 1 depends on xk and also yk, so they have an interaction between them. So that is called Euler's method for 2 dimension, which can be easily done using a for loop. Okay, now if you think about it, there's another way to write it. And if you really write it down, we can actually do a nice job if we can rewrite the original thing to be. Of course, this is a vector function. And then what we can do is we can simply just write down y k plus 1 equals yk plus h tk yk. Here yk is nothing but the two values put together. Then this one looks exactly the same as the one-dimensional Euler's method, except you replace all the scalars by a vector. All right, so now let's try an example. Let's try a very simple example where we have predator. Okay, we will have dr over dt, which is r prime. We have df over dt equals alpha we take to be 2r minus 1.2 rf negative f plus 0.9 rf. Now we want to do this thing on 0, 5. We want to use, let's say, I want to use 0.1. So let's use 50 points. Okay. So if you want to set up the Euler's method, oh, not to mention, we start with r0 equals 2 and the fox at 0 equals 1. Okay. Then to set up the Euler's method, you first take h. You want 50 points from 0 to 5. Then each step is going to be 0.1. Okay. So y0 equals 1, x0 equals 2, x1 equals x0 plus h, f t0 x0 y0, which is let's change it. I probably want to use r and f. r0 equals 2 and f0 equals 1. Therefore r1 equals r0 plus h times 2r0 minus 1.5 r0 f0. From here you can tell it's 2 plus 0.1, 2 times 2 minus 1.2 times 2 times 1, which gives you 2.2 minus 2.4. That's my first iteration. Okay, that's my R1. Now, R2 equals R1 plus H 2R1 minus 1.2 R1 F1. From here you can see we cannot proceed because this is not completely decoupled. The reason is we need F1. So whenever you finish one variable, you need to do the other variable before you can go to the next step of the variable. Therefore F1 is going to be negative F0 plus 0.9 R0 F0 equals negative 1 plus 1.8. Yep, 0.8. So at first you can see both of them actually goes down from 2 to 1.98 and from 1 to 0.8. But once you have that, you can plug in 0.8 here, you can plug in 1.98 here. And use a calculator, you can just keep proceeding and keep going. Once you have that, you can have F2, using the same analogy, and then after that you can do R3, F3, and forever. All right. From here you can see this is a easily replicable for loop we can write. So let's write it down for this one. Okay, here. Let's take 100 point. You can see it's not good. So probably we want to do a 1000 point. Okay, this start to match the pattern we anticipated by solving it analytically. But now you notice something. That is, this is a little bit different from what we had before when we used the careful method. Because before, it's a periodic behavior, but the period does not increase. The amplitude does not increase. But according to what we did here, it first starts from 4, and then as time goes by, it goes to 5. Maybe even if you give it more time, this one is going to keep increasing. Okay, which is not correct by our assumption. So that gives us, you need to use a way bigger number of points. And now from here, you can see the behavior is more reasonable. It stay at 4 and never become bigger. So before, clearly we used too few points. 1,000 point is not small. But still, we got something that we didn't anticipate. We find that maybe there is something wrong with our numerical method, and therefore we went in and did more points and find that, oh, finally, our anticipation was right. The previous one was giving us a wrong phenomenon, even though we already used 1,000 point. Then you start to wonder, is 10,000 enough? If I do 20,000, is the whole thing going to change? Again? Okay, or maybe I'm naive enough that if I just did 1,000, and I found this nice, beautiful curve, then I just trust it. Then my report is going to say, well, they are going to have a periodic sustainable pattern, plus both population is going to grow, which after we investigate it is clearly a wrong conclusion. But if you just trust your forward Euler's method, now that will be what you write down. Another more straightforward thing for you to see is harmonic oscillator. Before we do this, we know this is going to be a sine cosine. Okay, so therefore you are supposed to have a wave, and the wave should have a constant amplitude. But if you just do 50 points with this from Euler's method, this is what you're going to get, which you may still say, well, that's all right, because clearly once I see that, I will know it's wrong. But then if you bump everything up to 500 points, which is already a lot, and you receive a nice graph, do you trust it? Are you going to write down the report that my oscillation is going to keep going, plus it's going to oscillate harder and harder, which means the total energy is actually increasing? If you don't know anything about the physics, and you just look at the differential equation, and you just check the work, you may very likely to report this, because this looks reasonable. Okay? But once you know the physics, you know this is wrong. So, maybe 5,000 points. Now it looks more right. Okay, it's not amplified that much, but still amplified. So maybe you won't get anything stable until you bump everything up to 50,000, which is already a lot. Now, telling by my eyes, I couldn't tell the difference. So maybe the amplitude stayed constant. And of course, if I have several things to do, I will always trust the one with more points. So this is probably the phenomenon I'm going to get. All right, so from here you can see the forward Euler method is easy. But when you do it in 2 dimensions, even actually in 1 dimension, you will also have some phenomena. That is, the scheme is not stable. Sometimes if you just do it, it will give you some ridiculous answer. Of course, you know you're wrong, but sometimes it will give you something which is relatively reasonable. It's like, you're going to be oscillating, okay, but it's going to be bigger and bigger, which looks smooth and nice, but clearly it's also wrong. So when you have something not stable, what can you do? The first one is, you should know the physics. Then you will know, okay, even if I see some wave like that, I clearly have something wrong. Therefore, I need to increase my number of points. Okay, my method does not converge at all. Ahead of time. Okay, because the oscillation should not add to the energy. Of course, this is a luxury. Usually, in most of the cases, we actually do the reverse. We only can write down the differential equation, and we have nothing to analyze it mathematically. Therefore, we just want to run the numerical simulation to see what's going on, to give us some idea how the system is going to behave. So this is a luxury, not always doable. Second, you can have accumulated error, which you have already seen. Accumulated Remember, the oscillation at first is actually here with a +4 and -4, and then it goes to 5. So at first, the first oscillation is accurate. It's all the oscillation after that become more and more unreasonable. Okay? So usually a phenomenon you're going to see is, as time goes by, you should trust the front more than the later. Okay. Number 3 is somehow design the numerical method to be stable. So basically, we only introduced one numerical method, which is called forward Euler method. The reason we introduced it is because it's the easiest. There are other designs of method which will actually give you some stability, which means even for a very big h you pick, even though it's not going to be super accurate, but it will have the correct trend. Okay, you may have something which is very bumpy, which is not even smooth because you only picked a few h. But the horizontal asymptote, the horizontal amplitude is going to stay between -4 and 4, which is actually the correct range. Okay, so stability is a big issue to concern when you try to design numerical method. What you just witnessed in Euler's method is a classic stability problem. That is, when your h is not small enough, it actually gives you a wrong solution. Okay, it only starts to behave the way it should be when h is sufficiently small. Okay, and beforehand, there's no way you can know what do you mean by sufficiently small. Is 0.1 enough? Is 0.01 enough? Well, it varies from cases by cases. So you probably want to study, like, given a numerical method, for which level of h are you supposed to get something reasonable? Okay, and of course, when you design it, you are hoping that I want to design a numerical method such that it converges even for very big h. Because again, you don't want to take small h. You don't want to take h to be too small. Because if you have a long interval and a very small h, that will clearly give you a lot of computational request, which is harder and harder for a computer to perform. For example, if you want to study what's going on within the next 24 hours, let's not say 100 days. If you take your step to be 0.1, okay, which is going to be 1,000 points. But if your stability of your algorithm requires h to be less or equal than this, that will give you this many points for the method to start to work, not to mention to achieve a decent accuracy. Okay, now you can imagine if you want to do a simulation for 10,000 years. That's going to be the points, even though you take 1 day as a time step. And clearly, your method usually does not converge if you just take 1 day. Usually, you should take it to be like, less than 1 minute or something like that. You will have too many points to do. So if you design an algorithm such that it will converge for big h, that would be a big advantage. All right, so stability, I will just write it here. The algorithms converge for small h. That's what you're looking for. Okay, that means it gives you reasonable answers even when h is big. Okay, for more, Google it. It's not the concern of this class. And again, MTH 371, Introduction to a Numerical Method, will tell you more about how to design the algorithms and how to analyze the stability. Cool, that's all for today.